Swayam Prabha. Digital India. Educated India.
Welcome to this course on transition metal organometallics in catalysis and biology. We will be talking about olefin polymerization in today's lecture. We have started this topic in the previous lecture where we had just given a brief introduction about olefin polymerization reaction. Now, to begin with, it is important to note that as far as the olefin is concerned, their oligomerization as well as polymerization are both very important industrially in terms of large scale synthesis for various applications, the ranging from anti-knock reagents to detergents to even materials, polymers for material applications. So, as far as the olefin is concerned, they are both the processes oligomerization as well as polymerization are of substantial interest. Now, in this context we have discussed various forms of oligomerization reaction in the previous lectures and then started moving on to olefin polymerization. Now, with regard to the olefin polymerization, what we have learned that this is a very big scale industrial process where about 70 megaton of polymers are produced annually. Now, these polymers that are produced annually using olefin polymerizations are very diverse and require a detailed understanding of structure activity relationship SAR structure activity relationship in order to design a catalyst better suited for delivering polymers of particular need and demand. Now, the last thing which we had discussed in the last lecture is also about this mobility segment mobility, which is related to the extent of branching and cross linking present in the polymer backbone that sort of defines the type of material that one becomes. So, larger amount of segment mobility or branching could lead to development of softer polymer materials, whereas linear long chain polymers would give rise to more brittle and hard polymers. Now, in today's lecture what we are going to do first is to look at the various classifications that have been reported for these olefin polymers and then gradually go over the types of polymers that are known or have been named based on their different properties and classified based on these properties, and then slowly we will move on to various kinds of ethylene based polyolefin based polymers and then to polypropylene based polymers and then based on the classification, and then we will look into the mechanism and examples related to this polymerization reaction. So, to begin with let me just talk about various kinds of classifications of polymers that are conventionally used. The first one is thermoplastic materials. Plastic materials, exhibit shape stability under short term strain. However, upon warming, they are easily transformed into plastics. Now, what is a plastic in polymer jargon? Plastic means easily shaped, that is they can be changed to a shape of desire without much strain. So, that means they can be deformed, and once deformed, this plastic material sort of retain the final shape easily, that is easily shaped or deformed. So, what does plastic mean? That plastic material are easily deformed, easily changed into another shape. So, that means that plastic material do not have much memory of their own. So, they cannot come back to their original state after the deforming force is released, whereas reverse of plastic material are elastic material. Elastic material are the material which can be deformed easily. However, once the deforming force is taken off, elastic material has a memory and it comes back to its original shape. So, difference between elastic and plastic is that plastic material has no memory. However, elastic material can easily deformed but has a memory. That means, when the deforming force is taken away, an elastic material could remember its original shape and gets back to it, whereas a plastic material can also be deformed easily. However, when the deforming force is taken off, it retains the deformed shape. So, it has no memory, that means it does not go back to its original step. So, at higher temperature, these thermoplasts are plastic, and this change is reversible. And this change is reversible. Thermoplastic materials are built from linear or slightly bleached polymer. Plastic materials are built from linear or slightly branched polymer. With low segment mobility. And so, these are these thermoplastic material are not branched or slightly branched, or mostly linear. So, their segment mobility is kind of not too much and usually are low. And for this material the working temperature is lower than melting temperature. That means, the crystalline part phase of it or lower than melting temperature or the glass transition temperature. That is the amorphous nature. Now, at this point it is to be noted that polymers are large molecules and they are different from small molecule monomers. For example, for a small molecule it is important that the small molecule will have a unique molecular weight as well as a unique melting point. So, and often melting point is a method which is often used to characterize the purity of small molecule compounds by looking at its melting point. If the melting point transition is sharp, it is assumed that the compound is pure and also the melting point is characteristic of the compound. However, these two properties, that is the molecular weight which is unique to compound as well as the melting point also unique to a small molecule compound, are however different when it comes to polymers. Now, one thing which is primary difference is polymer for a polymer having does not have a single molecular weight. Usually the polymer produced have a range of molecular weight and they are usually given as a statistical distribution in terms of weight average molecular weight or the number average molecular weight. So, here is the first distinction between a polymer molecule and a small molecule compound, that a small molecule compound will have a unique characteristic melting point, whereas a polymer molecule will have a range of melting points and melting points may be different depending on how you measure them. One range of melting point can arise from their weight average molecular weight and the other range of melting point can arise from their number average molecular weight. So, polymer has may have many molecular weights, at least 2 molecular weights. Sometimes if the measurement is done through density, then the density average molecular weight. So, there are there is no unique molecular weight to polymer the way it is there for small molecule. Secondly, the second difference is that the polymer chain may have regions which are crystalline in nature, that means the chains are all stacked up in ordered fashion, whereas there may be regions where the polymer chains are random and completely disoriented. Now, depending on this region, the region in which the chains are very ordered and crystalline, so they show a transition, phase transition, which is called melting temperature, and the region where and this melting temperature is sharp for crystalline region, a sharp phase transition, whereas the region which is amorphous, where the polymer chains are not oriented in any particular direction or more random and disoriented, they do also show a particular transition, and these are not very sharp, they are generally broad, and these are called glass transition temperature. So, unlike a small molecule which can either be crystalline or amorphous in nature, polymer can be both. Polymer can have both crystalline domain as well as amorphous domain in it, and polymer may exhibit 2 transition temperatures, one is melting temperature, the other is glass transition temperature. And The third thing is the fact that the glass transition usually occurs at a lower temperature than that of the melting temperature. So, these are some of the unique features or attributes of polymers which distinguish them from monomer. Now, thermoplastic conditions for working for use of thermoplastic is that the working temperature in this context it is to be noted that the working temperature for thermoplastic material is lower than both the melting temperature as well as the glass transition temperature of the polymer. So, we come to the next classification which is duraplastic materials. These duraplastic materials maintain their shape upon extended period of strain. Or at high temperatures. And these these duraplastics are usually formed from prepolymers which are what is a prepolymer? Prepolymer is some naturally occurring polymer like rubber and so on and so forth which are cross linked or joined together through cross linking process called cutting, and these are also known as thermosetting materials. They are formed from prepolymers like rubbers, through thermal cross linking. Process and this process is irreversible. So, if we take some prepolymers and heat them then they become cross linked and they become duraplastic materials, and this process is usually irreversible. This cross linking of prepolymers to give duraplastic is usually a irreversible process. For duraplastic also for duraplastic materials the segment mobility is low. Is very low due to the presence of fine meshed cross linking covalent bonds. and because of this reason duroplastics are often amorphous and rarely crystalline. So, the first we had seen thermoplastic material, then we come across this duroplastic material. They can maintain their shape upon extended period of strain or at high temperatures. They usually are formed from prepolymers through thermal cross linking process. Also this duroplastic material has low segment mobility due to the presence of fine meshed cross linking covalent bond. However, duroplastics are rarely crystalline polymers. Next in this classification comes elastomers. Elastomers are applied above glass transition temperature. And they are deformed through applications of force. They are deformed through applications of force. However, upon removal of stress, they return to the starting state with maximal conformation entropy. So, this is what we just discussed that they sort of have a memory. So, the difference between elastic nature and the plastic nature is that like plastic nature, materials are easily deformed through application of force. However, upon removal of the stress, they return back to the starting state with maximal conformational entropy, as if they have a memory of their initial shape, and they come back to that shape when it comes to these elastomers. Elastomers are also formed by cross linking prepolymers long chain prepolymers and the degree of cross linking is wide meshed. is wide meshed. And so, what is the difference between elastomer and the duroplast is that duroplast also are formed by thermal cross-linking of prepolymers. However, in case of elastomers, this thermal cross-linking of long chain prepolymers are done, and the other difference is for duroplast that this cross-linking is fine meshed, whereas the degree of cross-linking is wide meshed in terms of elastomers. Another important attribute of elastomers is that elastomers exhibit high segment mobility. Elastomers exhibit high segment mobility. That allows a parallel alignment of building blocks under tensile stress. So, now the last important property or difference between elastomer and the duroplast is that duroplast has very low segment mobility. On the contrast, elastomers have very high segment mobility that allows a parallel alignment of building blocks under tensile strain. So, with this we come to conclusion of today's lecture. In today's lecture, what we have done is we have looked into classification of olefin polymeric material based on their properties, and to begin with we had covered three different kind of polymer classification. One is called thermoplastic material. These are the materials that exhibit their shape under short term strain. Upon higher temperature they become plastic. Then we have looked at duroplast. Duroplast materials maintain their shape upon extended period of strain or at high temperature. And lastly, we looked at our elastomers which operate above glass transition temperature. These are easily deformed, but upon removal of the deforming stress, they go back to their original configuration and retain their shape. So, we had seen how these materials are formed usually by forming cross linking between prepolymers by heating, and then we have also looked at how finally they are meshed in order to retain the classification that category that it belongs to. So, with this I come to the end of today's discussion. We are going to talk more about the classification of polymers before we look into polyolefin and polypropylene in terms of the synthesis and the mechanism. So, there is a lot of excitement ahead in this topic of olefin polymerization. So, with this I again thank you for being with me in this lecture, and I look forward to discussing more on olefin polymerization when we met next. Till then, goodbye and thank you.